Hello, am I audible now?
Yes, sir.
Yes, sir.
So, shall we start, Dr. Mahit Kumar? You want to?
Vanid, Dr. Nisha will introduce to Professor Swagatam Das. Yes, ma'am.
Okay, thank you, sir. So good morning, sir, and good morning to all the participants. It's an honor to introduce her. For our today's session, we have Dr. Swagatam Das, sir, with us. He had his PhD degree as well as his BE and MTech from Jadavpur University, India. He is currently serving as Associate Professor at Electronics and Communication Sciences Unit of the Indian Statistical Institute, Kolkata, India. His research interests include evolutionary computing, pattern recognition, multi-agent systems, and wireless communication. He has published more than 300 research articles in renowned peer-reviewed journals and international conferences. He is the founding co-editor-in-chief of SWAM and Evolutionary Computation, an international journal from elsewhere. He has also served as and is serving as the associate editors of the Pattern Recognition Elsewhere Journal, Neural Computing Elsewhere, Information Sciences again elsewhere, IEEE Transactions on Systems, Man and Cybernetic Systems, IEEE Computational Intelligence Magazine, IEEE Access, and so on. He is also an editorial member of Progress in Artificial Intelligence Frontier, Applied Soft Computing Elsewhere, Engineering Applications of Artificial Intelligence Elsewhere, and Artificial Intelligence Review Frontier. He has also been associated with International Program Committee and organizing committees of several reputed international conferences, including IEEE CEC, IEEE SSCI, GCCO, and SEMCCO. He has acted as guest editors for special issues in journals like IEEE Transactions on Evolutionary Computation and IEEE Transaction on SMC Part C. He is also the recipient of Young Engineer Award in 2011 from the Indian National Academy of Engineering. He is also the recipient of the award in 2015, Thomson Reuters Research Excellence for the Excellence India for the highest citation or the highest cited researcher from India in engineering and computer science category between 2010 to 2014. So, sir, it is a privilege for us to listen to you. I hope the participants will be enjoying the session with you. Sir, over to you now. Thank you.
Yeah, thank you very much for the long introduction. I will share my screen and show you the slides. Today, the topic of the presentation will be deep generative neural networks, which is one of the most state-of-the-art area in the whole realm of deep learning. So, if at any point of time you cannot hear me or you cannot see the screen, please let me know. So I hope you can see these slides. I will make them full screen.
Yes, sir.
Yeah, thank you. So as you can see, the title of this talk is about deep generative adversarial networks, which in short are called GANs, which were first published only 6 years back, 2014. And by now, they have occupied a very strong foothold in the paradigm of machine learning. And we will see that neural networks do not only classify objects into proper categories, but they can also generate artificial pictures, sounds, texts, etc. And they can also be used for this sort of artificial synthesis of very realistic abstraction of objects, which means photographs, texts, etc. In this lecture, we will be precisely confine ourselves to images and mostly focus on this generative side of computer vision. These numbers are called features by machine learning people. They are called variables by statisticians. These numbers sit together in the form of a vector, or it can be a matrix, or it can be a sequence. These days, in advanced machine learning, it can also be a tensor. So X is that mathematical structure which contains numbers that best describe an object. For example, iris flower is an object which comes to a human being in terms of its fragrance, color, odor, appearance. But to a computer, in machine learning, this phrase, machine stands for computer. So to a computer, the same flower comes as a vector of 4 numbers, which are basically 4 structural measurements by botanists under the name of sepal length, sepal width, and petal width. So sepal and petal, you know, for a flower. Essentially, this vector, each such vector corresponds to a physical object or flower, and each such vector physically, abstractly, mathematically represents that flower to the computer. Now, supervised machine learning is about how to translate human experience into a computer or a machine, such that, based on the experience, the machine builds up a function f of these feature vectors x, such that when a new feature vector comes, you plug it inside this prediction function. This function is actually the main machine learning model. Statisticians call them model, or we can call them classifiers, we can call them prediction functions, various names for the same entity. So we plug in the vector x into f as an output. The vector return that the function returns us in the correct category of that object. These categories are initially pre-specified by the user or by the human expert. But okay, you have 3 types of iris flowers, so each flower must belong to one of these 3 racks in the almirah of your iris flowers. What are these racks? Iris setosa, iris larkinia, and iris veriscala. And initially, the human expert will label these some of the flowers manually. Then, based on those labeling, this function has to be prepared by the machine or computer. It's just like when all of us were young, age 3, 4, 5. My mother used to point to a kid's storybook and say, kids picture it and say, look, this is a cat, look, this is a dog, that is a rat, etc. After a few rounds of such training, one day when I go on the road with my mother and there is a creature passing by me, along with stare, I would yell out, "Mother, look, that's a dog." So what did I do? Based on the experience given to me by my mother, I took a decision about the category of the creature which just passed by me. I said it's a dog, not a hippopotamus, it's a cat. So this is learning. Capability of taking a future decision based on past experience. In case of supervised machine learning, we want the computer to do the same thing, and the experience is provided to the computer by training data. What is this training set, training data? Training data is basically a small part of the entire data universe, very small part, very limited, say, data items which are manually labeled by a human expert. So these x1, x2, up to xn, these are the initial points manually labeled by a human expert, and y1, y2, y2, these are the class levels provided by the human expert. Based on these limited training set, this sort of a function has to be created, and when a new point comes, a new data item comes, we must rely on this function to tell whether to which particular category this new point x must belong. This new point is called a test point or a query point, which is unseen, initially unseen. So that is basically the supervised machine learning business. So when we are doing image classification, different images, features of different images, usually features of the numbers which characterize each of these objects must come and characterize each image. And then we put these images inside the functions, and then the functions should return us the proper category: image of an apple, image of a tomato, image of a cow, etc. So, in short, this is the whole thing. And very often, for example, in a computer-assisted diagnostic system, you have images of breast mammogram, digital mammogram images. So once you have these mammogram images,
sorry to disturb you, sir. I think there is some echo. Actually, voice is not so much clear. Actually, I think there is echo.
that may be due to connection. I cannot really help it. I can try to reconnect somehow. But that's why Google Meet is...
Voice is coming, but coming with some echo.
No, sir, your audio is very clear.
But okay.
Hello? Yeah. I think now it should be clear. Right?
Yes, sir, it's fine now. Earlier it was having little bit disturbance at the background.
Okay.
Thank you, sir.
So as I am saying, so you hire an oncologist, and the oncologist is labeling 100 such mammograms manually and just looking at them and trying to figure out whether there are off-white patches inside the mammogram, which is very, sometimes a human eye can miss that. So he tries to detect such off-white patches inside the mammogram. These patches are called microcalcification spots, and they are a clear indicator that the breast cancer, in fact, breast cancer has started. Very early stages of breast cancer, breast tissue carcinoma. So the doctor labels these images. So maybe you can hire an oncologist is very costly. So his expertise is very costly. So you can hire an oncologist for 1 hour, and within 1 hour he can label 60, 70 pictures manually. Then you need to give these labeled images to a machine, each image transformed into a vector of features and the corresponding class label to a computer. The computer must develop, or the computer must be programmed by using the supervised machine learning algorithm such that next time when a new image comes in the form of such a vector, the machine must predict whether it should belong to the it should belong to the malignant class or benign class. That's the idea of supervised machine learning. And is it, in case of image, the question comes, is it really very hard? The answer is yes. When we look at an object like this, we usually perceive the wheels and the engine and the handles at once and just see it's a motorcycle. We label it as a motorcycle. Human beings are terribly fast and very good at it. But what does the camera see? Or what does the camera record? The camera sees piles of numbers, as you can see here. If it's a color image, the camera will see 3 such, two-dimensional array of numbers. And these numbers, from these piles of numbers, it is very difficult to find out what the actual object is. That is, these numbers are the sensory device or camera recorded lowest level features. These are very close to the machine. Just like when you compile the C code in finally generated .exe file, this executable file is written in machine language code. And the machine language code is very close to the machine, very far from the human beings. You cannot really understand it. You understand probably the high-level language code, which is the C code itself, right? So when the camera looks at this, when the camera reports these piles of numbers, two-dimensional arrays, these are the lowest level features, and abstract high-level features must be developed by suitable linear, non-linear combination of these lowest level features. These abstract and high-level features will be helpful for specific classification tasks. So when you look at the picture of your friend on Facebook, do you look at it in this way? The top left corner pixel is 232, beside that 146, beside that 98. No. You immediately capture the abstract and high-level features in the face of your friend. Wide forehead, thick mustache, cut mark on the chin, etc. We want a machine to loosely follow this remarkable capability of human visual recognition system. That's how all this deep learning business started. Okay. So suppose I mount a camera on the doorway of my garage, and then I represent each image in terms of these two pixels, pixel 1 versus pixel 2. So I just sample two random pixels from two fixed locations of each image and plot them along x and y axis. What will happen? These two pixels will have similar values for wide range of images. As a result, cars versus non-cars. Why I am mounting a camera on the top of my garage, gateway of my garage? Because I want to see that only cars are permitted inside, not an elephant walking in or a cow walking in, etc. So, cars versus non-cars. The major objective of the camera is to take images. Based on the images, there might be a small embedded processor which will do this classification, and whenever a non-car entity is walking in, the elephant is going into the garage, it should sound some alarm or should connect to some alarming system, alerting system, right? However, in this situation, cars and non-cars will be fully mixed like this because these two pixels will have similar values for them. So it will be a khichdi, and you cannot draw any Lakshman Rekha, you cannot draw any line of demarcation between the two classes to actually separate them out. So might be you could have done a better feature representation by sliding a 3x3 or 5x5 window over the image, and this window would have such coefficients which we will call convolutional filter coefficients later on. So this window will contain such coefficients that when this window is slided on the picture, as soon as the window captures such kind of a handle-like structure, it records a very high number. So it could be called a handle detector. Similarly, another window which will be traversing on the image, as soon as it captures a wheel-like shape, it will record a very high response, and we can call it a wheel detector. So response of these two windows, gross response of these two windows when they have traversed all over the image in a horizontal shift left, shift right manner. And then if we record the responses, handle detector versus wheel detector, we will see the cars coagulate far away from the origin, non-cars accumulate very near to the origin, and we can really draw a line of demarcation between them very easily. So a lot depends on better feature representation. How you are abstracting a physical object to a machine, how you are representing the object in terms of numbers, and these numbers must be very cleverly crafted or chosen such that they capture the most important characteristics of the particular entity for a specific classification task. Here, in fact, what will be the classification task is very much this context of classification is very much dependent on the users. So here, my objective was to demarcate between cars versus non-cars. So detecting handle and wheel are good enough. We can neglect all other details. If some entity has 2 wheels or 3 wheels, handles, etc., it must be a car. Or steering, something like that. That's another wheel display. So these days, when we have very related images in Plethora, it's very difficult to, especially if the images are very close to each other and share lots of commonalities, common features, it becomes very difficult to classify them. But human beings are rapidly good at it. So you can look at these images and immediately tell me which one is a sheepdog and which one is a moth. Similarly, human beings, how much time you guys are taking to look at these images and just understanding which one is a puppy and which one is a backyard. I think very, very small time you will need. But if you want to do a computer the same thing, it's a simple two-class classification, but the images are very much related. Not only human brain can immediately visually recognize these two different categories. Here also you can see barn owl or apple. But also the human brain can capture the features, the abstract and high-level features, not those pixelated numbers. So human brain can also recognize based on which features this classification might be done. So if you look at the owl's face, you will see there is a huge gap, long gap between the two eyes. Whereas in the apple, the two seeds are very close to each other. The apple has a ridge-like structure, but owl also has a sharp nose-like structure here. So by looking at these, you can immediately say which one is an owl's image and which one is an apple's image. Similarly, which one is Chihuahua, which one is this dog puppy, and which one is a muffin. For the dog puppy, you also recognize that the eyes and nose, these three dots, are arranged almost regularly. But the cherries in the muffin are not arranged in a regular fashion. Am I clear? So when you look at these categories, your brain very quickly analyzes the most important features based on which you will mark which one is dog puppy and which one is muffin. To do the same thing by using a computer or a machine is a tremendously difficult task. Therein comes the deep learning. The last 40 years of research in computer vision has been devoted to this feature extraction problem. How we can, combine the measured pixel level features in various manners to generate other high-level descriptions of the image, which can be translated into numbers that can be used for right categorization. How we can do that? This was one of the major quests in high-level image interpretation, computer vision, etc. Deep learning comes as a great assistance to this. Deep learning is just like this straw. This modern crow will use a straw to suck up the water from this picture instead of putting these stones one after another and waiting when the water comes to the mouth of the picture. Deep learning is just like a straw. So what does it offer to us? This slide clearly explains the same thing. So as you can see, the traditional machine learning cycle, we have an input. There is a feature extractor, human feature engineer or feature extractor. That's an individual. Such feature extraction techniques always resulted from individual results group. Those scientists became very famous overnight. But unfortunately, most of the handcrafted feature extraction techniques, let's say just for image, speech has another group of extraction techniques, text has another group of extraction techniques. Just for image, if you look at it, there is scale invariant feature transform or SIFT, histogram of oriented gradients, HOD, there is text storms, there is RIFT, so many types of feature extraction techniques, DCT, DWT, discrete wavelet transform and its variants. However, none of them are universal. You cannot blindly apply any one of them to your image. You must understand that these extraction techniques are specific. They will work very nice on specific types of images, but not on the other types. And how many types of images are there? So many. Okay? Natural cynical images, SAR images, satellite images, biomedical images like CT scan, X-ray, PET scan. So many different types of images are there. And the same feature extraction technique will not give good result for all of these types. Traditional machine learning requires the human feature extractor first to do programming, compute, convert the initial low-level features into high-level features. Then these high-level features are fed into a classifier network, which will decide whether it's a card or not a card. Deep learning eliminates the need for this human feature extractor. A deep learning system is basically a system of cascaded layers of simple computing nodes or computing units. These simple mathematical processing units are called neurons, and these layers are arranged in a cascaded, series-connected manner. The information flows from initial layer to next layer to next layer. So input to a one layer is basically the output from the earlier layer. And in what information flows, you can see these links between these nodes. What are these links? These links are pathways through which initially the recorded low-level features flow like a signal. And while flowing through these links like a signal, each link has a weight. So that weight controls how much the signal will be amplified or attenuated. And in different nodes, these feature signals, these features behave as signals. So these feature signals are actually linearly and non-linearly combined, convoluted, going through very nonlinear operations, finally provides the neural network the very important and very much distinguishing features which can categorize between various groups of data for specific classification tasks. That's the idea of deep learning. There are two deep inference models. One is the predictive deep learning model, which perfect example of which is the convolutional neural networks or CNNs, and various variants of CNN. So the predictive or the discriminative model, we also call it discriminative. This discriminative model learns to put a line of demarcation, which in the easiest form is just like a straight line. If you have gone through, some of you are aware of the linear SVMs. The linear SVMs also do the same thing.
Sir, can you feedback link?
Yes?
Sir, can you please send me the feedback link?
Please share the
So you mean the voice is having feedback still, right?
participant, please don't disturb to sir, please.
Sir, then send me the feedback link chat box.
Yes, we will send you feedback link. Please write in chat box. Don't disturb to sir, please. Sir, please
Yeah,
continue.
I can see there is some voice issues, but this might be due because of the internet connection, and Google Meet is recently very bad. So you have to bear with me for this.
No, sir, it's working fine. There is no disturbance, I think, from.
For some participants, it might be due to internet connectivity issues. It's not due to the hardware.
Yes, sir.
But as you know, I mean, in this new normal, we can do very little about the connectivity issue. So in case of discriminative model, just like the linear SVM does, you just draw a straight line between the points from the two classes such that when a new point emerges from the blue class, it will be on the left side of your line. And this straight line or this discriminant function, we call it a discriminant function or decision boundary, it has a mathematical form. So when you plug in the features of your data point into that function, into that mathematical form, it either gives you a positive high number or a negative low number. By looking at what it returns, you usually decide from which class your data item came. That is the essential, that is how a discriminative model is made. But nowadays, the deep inference models are pertaining to generative learning and generative models. What are generative models? These models not only try to, for classification is a secondary task for these models. What they try to do is they try to approximate the underlying probability distribution of the set of objects. Okay? So you show it a set of objects or data items. It tries to estimate from which underlying multivariate distribution these objects have come. And this is an age-old problem in statistics. Statisticians are after this problem for the last 100 years or more, I think. I will give you 5 scalar numbers. Think of it. You might have seen this problem in many other occasions. I give you 5 or 10 scalar numbers, 2.8, 2.6, minus 4.2, etc. And I ask you, tell me the Gaussian distribution, give me the mean and variance of the Gaussian distribution from which these 10 numbers are most likely to be sampled. Okay? That is the density estimation problem. An usual way of doing this is to assume that these numbers have an IID distribution. IID stands for independent and identically distributed numbers, and then use some algorithm called MLE or maximum likelihood estimates. If there are hidden variables, you will use expectation maximization. That's an age-old problem. So what's new in it? The new thing is, instead of 10 scalar numbers, if I give you 1,000 multivariate vectors, multivariate means multiple components are there in the vector. Each component is basically the sampling of a sampled component of a vectored random variable. So if I give you 1,000 images, and these images are converted, into 1,000 high-dimensional vectors, and I ask you to provide me the underlying multivariate distribution from where these images might have been sampled, the problem becomes strikingly difficult, almost intractable by classical methods. That is where neural networks, and especially the deep neural networks, come into picture. And just 6 years back, from one Canadian research group began, or generative adversarial networks emerged, which provided strikingly good result in such scenarios. So, do you understand what is the implication of it? You are showing GAN pictures, many related pictures of bedrooms from certain categories. Suppose you are showing GAN lots of pictures of bedroom with different decorations, different linens, etc. After being shown 100 or 150 such bedroom images, GAN can actually estimate the underlying distribution of such images if it is properly trained, and then it can sample from that distribution. That means it can generate artificial bedroom images which appear to be very realistic, but they never existed on Earth. So to common man like us, everything comes from God or everything comes from nature. To a statistician, to a probabilist, every object is sampled from an underlying multivariate probability distribution. And if you can get a hold of that distribution, you become like God. Then you sample from that distribution and you can generate realistic objects, at least in picture. That's what GANs do. And they have very good uses. They can have very bad uses as well. We will come to that. So anyway, before I proceed into the technical part of GAN, this is what the deep neural nets in a nutshell. Before 2010, essentially, 1980s era neural networks, still there are very classical-minded people who work with this sort of neural networks with one single hidden layer. And you see this picture, there is a single hidden layer between the input and output layers of this neural network, which is a very loose imitation of human neural circuit, very loose, almost baby steps. And these links carry signals from one node to another. And these links also have associated weights to boost up the signal or to attenuate the signal. Deep neural networks are characterized by the presence of multiple hidden layers. These hidden layers are responsible for combining lowest level features gradually into more abstract and high level features. That's why the learning that happens through the hidden layers, at least in the initial stage, is also called representation learning. So the network is learning to properly represent the data. Okay? And there are multiple hidden layers with hierarchical features. These, for example, in case of a face recognition system, starting from the pixels, they combine the pixels to identify the edges. By combining the edges, they try to identify the body parts like eyes, nose, ear, etc. Then by combining these body parts suitably, for each face class, one prototype, abstract prototype will be stored in the network. And when another representative, another image from the same face class comes to the network, which was not included in the training set, the network can quickly match this image with the stored prototypes, and the closest match class will be inferred. It's just like when my mother was pointing me to the pictures book and saying, this is a cat, this is a dog. So the app draws texture, size, shape of that creature was somehow registered in my neural circuit under the tag word of dog. When I knew such a creature, knew such animal passing by me, I could very quickly match with the prototype stored in my brain. And through that match, it happens in fractions of even a microsecond. And as soon as it happens, then I infer, okay, this is a dog which passed by. That's how it's a very loose imitation of this remarkable decision and recognition system in human visual cognition. So the 2012 breakthrough in predictive deep learning came through this particular paper, which now has 70,000 plus citations. This is somewhat older statistics. And what they do is they had this paper specified, this paper actually proposed a deep neural network for classification of the famous ImageNet dataset. ImageNet dataset was compiled in the Stanford University by Fei Li and her students over a span of 5 years. It includes 1.5 million tiny images taken from the internet, distributed over 1,000 plus classes. And these are the images of a coffee mug, a bird flying, a road, a tree, etc. These images, this is a large scale, and these images were put forth as a competition under the tag word of large-scale visual recognition challenge. Before 2012, 2 years of the competition, classical machine learning methods yielded an accuracy of 70%. 2012 deep neural network, this particular paper authored by Geoffrey Everest-Hinton, one of the godfathers of deep learning, revolution, and his two students. This paper brought down the error to 16% and the accuracy went up to 84%. And that was the beginning. From this paper, the entire craze about this deep convolutional networks for image processing and classification started. And when such a craze starts, new things emerge out very fast. Lots of research funding started to pour in from leading industries like Amazon, Google. Google found its DeepMind. Then came Facebook. Then came Netflix, Uber. So lots of giant software industries, Microsoft, all of them started to invest huge amount of money behind this. And within 3 years, there was, if you look at this, so see the number of hidden layers in the 2012 network was only 8. Only 8 layers were there. That mounted to 152 layers in 2015. Residual network, or ResNet. This ResNet brought down the error to 3.5%, and the accuracy went up to 96.5%. That's a remarkable progress, because in the image classification problem, the human level accuracy is of the order of 97%. If you are a healthy human being, if you are not drunk, and if I show you images at a rapid succession, maybe out of 100, 3 images you will mess up. For all other images, you will properly identify what the image is, right? That's what human level accuracy, and it was touched long back in 2015. Now the accuracy in ImageNet is more than 98, I think. So what happens inside a convolutional neural network is basically convolutional neural network, or CNNs, compress an image, and they accept the image as it is, as a two-dimensional array, through the operations called convolution followed by max pooling or pooling. There are several subtypes of pooling. Through these two operations, the image is actually gradually compressed in the form of lots of feature maps. These feature maps contain very few numbers compared to the whole image. And these numbers finally packed into a vector. This is called a codebook vector. This vector contains such numbers which best summarize the abstract and high-level features of the image for a specific classification task. These numbers do not fall from sky. The network learns them by back-propagating the gradients of one single error function at the output. That's the beauty of it. We are using the same minimum squared error or cross entropy type loss or error function at the output based on the gradient of the single error function, all these convolutional filter coefficients, these are the feature detectors. I was talking about angle detector, wheel detector. So these convolutional filters try to detect, they have certain coefficients inside them, and these coefficients are adjusted or tuned, that is basically the learning process, such that finally these convolutional filters, these are 3x3 or 5x5 masks, when they traverse over the image, they capture the most distinguishing part of the image. For example, look at this particular image. Nowadays, so look at this particular image. It's a bird's image. If I want to distinguish a bird from a non-bird, why should we consider all these background pixels, whatever lies in the background, a tree, some other human beings, whatever? They doesn't matter. These things don't matter. Only thing that matters is whether this creature has feathers or a beak. If it's, because my objective is to distinguish birds from non-birds. So presence of a beak, this is the most important feature. All the rest can simply be ignored, right? And the convolutional filters try to capture, try to detect these most essential features from an image. They learn it, and this learning process comes from an optimization. So essentially, given a high resolution picture, nowadays you have 9 megapixel cameras. Every one of us has 13, 14, 18 megapixel cameras. So when you click an image with a 9 megapixel camera, you will have 3000 pixels along the length and 3000 pixels along the width. So you have 9 million pixels. If you convert it into a vector and try to process that vector, it would be hugely computationally demanding. So convolutional net accepts such a high resolution picture at its input and converts it into a very low dimensional final feature vector, high level feature vector, not low level, comprising of 2000, 3000 features from 9 million to 3000, suppose. Then that feature vector is actually used for the classification in the final fully connected layers of a convolutional neural network. What if I reverse the flow? So convolutional neural network converts an image into a vector. High resolution full visual image into a vector comprising of such high level features as numbers as its components, which best describe various aspects of the image for its classification. So that vector is called a code vector. If we reverse the flow of the CNN, then what will happen? We can give as an input a code book vector, a code vector, and the convolutional neural net. Now we will call it a deconvolutional neural net. So this deconvolutional neural net can create an image out of it. This is one of the very interesting parts of GAN. So therein comes the GAN, Generative Adversarial Network. As you can see, the paper came in 2014 NIPS conference. And it has by now 20,000 plus citations. This is again older statistics written here. So GANs were trained with medieval period portrait artists' pictures, and after such training, GAN drew its own medieval charcoal drawn portrait of this particular picture. And if you look at the sign, there is a signature of the artist. The signature reads Generative Adversarial Networks. So this painting was about to be auctioned in USA for a price of $413,500 US. So realistic. So what is this? How GAN functions? Let's try to at least understand a little bit of it. The probabilistic generative models actually take observations from real worlds, and then they try to generate synthetic observations. Observations, data items, patterns, all are same. These are abstraction of physical objects. So from real worlds, some feature vectors are coming. These feature vectors are abstraction of the physical object. Or image is also an abstraction. And the model tries to generate artificial synthetic observations, and the goal of the modeling is to match them such that the two probabilities can be very close to each other. And the idea is essentially how you can convert one simple probability distribution like a uniform distribution to a more complicated Gaussian distribution or mixture of Gaussian distributions. That's the basic idea. And the neural network acts as a converter of a simple probability distribution into a more complicated distribution which best mimics or best estimates the underlying distribution of a specific type of objects or a specific type of images given as a training set. Let's try to understand this idea. You have a neural network. Suppose you have a simple feed-forward neural network. This neural network has 25 input dimensions and 25 output dimensions. So it maps from R25 to R25. Now you provide the neural network with a 25-dimensional random vector, completely random. Each component can be 1 with 50% probability, 0 with next 50% probability. So it's a completely random vector of zeros and ones. By the way, here I can interpret this 1 as a full white pixel and 0 as a full black pixel. And since it's a 25-dimensional vector, I can always arrange it into a 5x5 small image. Okay, so when I arrange it like that, the small cells which are assigned with 1 will be completely white, the other cells will be completely dark. Now I provide this random vector to the neural network. The neural network processes its components and returns me another 25-dimensional vector. I pack it in the form of an image. I also have 2-3 such small 5x5 images with me, which has a small dog-like shape in between, as you can see in this image. They have a small dog-like shape in between. The connected white pixels or the connected black pixels form a small dog-like shape. Now, if the image returned by the neural network is not having such a dog-like shape, I measured the difference of this image and the actual returned image. I measured the difference. Based on this difference, I go back and adjust the weights of this generative network. Based on the gradient of this difference of the two images, one coming from the neural network and one under my disposal, I measured the difference, especially when there is no dog-like shape. Then I take the gradient of that difference, go back and punish all the weights of the neural network, go on tuning them, and this cycle goes on and on. After this training process converges, what will happen? Whenever I will give random vector to the neural network, random 0-1 vector to the neural network, the neural network will learn how to arrange the pixels in suitable manner such that the output 25-dimensional vector, when converted into a 5x5 image, will have a dog-like shape in between. Do you understand? And when this happens, we will very dramatically, theatrically say, the neural network has learned the underlying distribution of the dog-like shape images. In a 5x5 small image, there is a small dog-like shape. So there is some distribution of this image also. It's a 25-dimensional multivariate probability distribution. And this generative network has somehow learned the distribution. So whenever there is a uniform distribution vector at its input, it is converting it into the distribution of these 5x5 images with a small dog-like shape. That's what it has learned. So this is how neural networks can transform one probability distribution into another probability distribution. This is the easiest way I can, because it's mathematically very involved. This is the easiest way you can visualize. So starting from a uniform distribution, it's converting into a more complicated distribution like this. So using the same idea, but in terms of an indirect training, there comes GAN. What GAN does is very unique. GAN has two distinct neural networks. One is called Generative, which is basically a convolutional neural network in reverse flow. That's a deconvolutional neural network, or it can be, if you are familiar with autoencoders, I don't know how many of you are. So it can be the decoder part of an autoencoder. For now, just accept that generator is such a neural network whose input is a code vector which can be generated from noise or uniform distribution, and whose output is an image. As I just said, the deconvolutional neural network very well does this thing. So this generator generates artificial images. Initially, when the generator has not got any training, it has not learned anything, it will generate ghost-like images or completely bad images. But then it has some feedback to receive from another neural network, which is called discriminator. The discriminator learns to differentiate between the real images at its disposal in the form of the training set versus the images generated by the generator. The discriminator usually provides a single scalar output. This scalar output is very near to 1 if it identifies the image as real, and it is very near to 0 if it stamps the image as fake. Okay? So GAN proceeds through a competition between these two neural networks. One is a generator and the other one is a discriminator. The discriminator is usually very simply is just a logistic regressor. It's a two-class classifier, usual feed-forward neural network, convolutional network, obviously, because we are dealing with images. The generator can be a deconvolutional neural network, and they are competing with each other. The generator tries to fool the discriminator tries to catch up the generator by assigning very low score to its output, trying to assign very low score to its output, and saying, hey, you have generated a fake image. So it's like the tussle, the tug of war between a group of police. There is a anti-corruption unit of police who tries to seize, fake currency notes. And then there are very clever groups of people whose main hobby is probably to publish very realistically looking currency notes which are fake. So the police initially is successful to catch a few of such people, put them in jail. But from the mistakes they made, the rest of the group of the counter of this fake currency producer group learns. And next time they are trying to produce more realistic fake currencies, which will be harder for the police to catch. So through this competition, both the neural networks are actually improving. Let me just try to tell you the basic idea of GAN and then we will conclude. The generator, as I said, basically can be the decoder part of an autoencoder. It receives, let's just look at it from this view. This is a system which receives code. Code means simply vectors of floating point numbers as its components. Each number should actually encode some high-level information. However, we just simply call them code vectors. They can come from, initially they can come from a uniform distribution, as was happening for the generative model 1-2 slides back. So codes are simply vectors. These vectors are provided to the neural network generator, and the generator generates images triggered by these vectors. Different codes will cause it to generate different images. So the images, each code is responsible for one image. Codes may be 2-dimensional, 3-dimensional, 3000-dimensional. It depends on the resolution you want from your GAN generation. So this is the idea. Given a specific code, the neural network generator learns to generate an image and tries to make this image as realistic as possible. This is for the generator part. But when you are using the same neural network as a classifier, then what you are doing, Google Meet doesn't allow us to slide change, to transit the slides very nicely. So when we have this neural network classifier, you provide an image to the neural network classifier, it generates the class level vector, which could be a one-hot encoding. If it is 1, then the Y1 component should be highest. So the classifier tries to match these two vectors as close as possible. That is the difference between neural network generator and neural network classifier. So the question is, where does the code come from? How the generator is trained? Now come to the discriminator. Discriminator is basically a neural network which mimics a function that takes an image as its input, X is the image, and assigns a real score to it as its output. So the output is a single real number R. So input is an image. So when this very realistic henshine image, cartoon image goes to the discriminator, it assigns 1. But when such a bad looking hazy image goes into the discriminator, which might have come from the generator, which is not real, obviously, the discriminator assigns it a very low score of 0.1. So discriminator is also called evaluation function, potential function, etc. Now the question is, can we use the discriminator to generate objects? The answer is yes. By using a roundabout path through the generator, by providing some feedback to the generator. So the general algorithm is given, so the discriminator training, how the discriminator can be trained. Given a set of positive examples, that means a set of real-looking images from the training set, let the generator generate a set of negative examples. That means initially the generator is untrained, unlearned. If you ask a 4 or 5 years old kid to draw some very realistic scenery, can the kid do that? He or she will draw some random lines on the drawing sketchbook because the kid is not trained in drawing scenarios, right? Same thing happens with the generator. Initially, the generator generates such very ugly-looking, unrealistic images, and the discriminator learns a 2-class classification between the positive examples taken from the training set of GAN and the negative examples which have been generated by the generator. So in each iteration, the discriminator learns to discriminate between the positive and negative examples. Now the generator can use, once the discriminator is trained, once one training cycle of the discriminator is over, the generator can learn how to generate negative examples, how to generate more realistic examples by trying to maximize the score of the generator, of the discriminator. So the generator uses the trained discriminator as its teacher, as its guide, who provides feedback, and the generator tries to adjust its weight so that it can maximize the feedback from the discriminator. So the generator now generates this X tilt, which is an image from the generator. This X tilt is generated in such a manner so as to maximize the score of the learned discriminator. So generating negative examples, the NM generator generates image. The image is provided to the discriminator. Now the discriminator is already trained. It has already passed through one training cycle. So the discriminator assigns a score of 0.13. This image is usually hidden. Now the generator is updated. Once it gets this bad score, the generator is updated. It generates a new image. So the discriminator is now assigning new score to the new image. Once the discriminator starts to assign very high scores to the images coming from the generator, that means the generator is now in a good shape. It has really learned to fool the discriminator. So now it is the time to update the discriminator. So once again, let us train the discriminator. This way, discriminator training, followed by generator training, followed by again discriminator training, then followed by again generator training. Through this intertwined fashion, the training of the 2 component neural networks in GAN goes on. The algorithm is initialize generator and discriminator. In each training iteration, sample some real objects from the actual training set at your disposal. The generator generates some fake objects which are initially very bad looking. The discriminator learns to distinguish between these 2 classes. Initially, that's a very easy task because the generated examples are very bad. So the discriminator learns to assign such scores. Once the discriminator has passed through its first training cycle, it is kept fixed. Now the generator generates images and the discriminator provides feedback for these images. Based on this feedback, the generator updates itself, learns to generate more realistic images. Okay. Now the discriminator is fixed and the generator learns to generate more realistic images. Next time, this improved generator is used for updating the discriminator. So the improved generator generates new images, discriminator again learns how to demarcate them from real images, discriminator improves. This is the learning cycle of the discriminator or D, and this is the learning cycle of the generator or G. These two learning cycles are very much related, connected with each other. One comes after the other, and then the next comes. This way it happens. Okay? So benefits of GAN, discriminator actually uses the generator to generate negative examples so that it can see positive examples from the training set. These are the realistic actual images, and fake images are coming from the generator. It tries to demarcate between these two images. From generator's point of view, it still generates objects from component by component, but it is learned from discriminator with a global view. Three scenarios can come in the training cycle of GAN. One is the false negative scenario. In the false negative scenario, the discriminator receives the real image and marks it as fake, assigns very low score to it. That means now the discriminator must be tuned. The weights must be adjusted because it is not doing the right thing. That's the false negative scenario. Then there comes true negative scenario where the generator generates a fake image. The discriminator says, yes, it is fake. So now the generator requires punishment or adjustment of its weights, which is done by using the gradients of the error function. Then there comes false positives. False positive means the generator generates fake image and the discriminator assigns a very high score to it. So who is doing that? The discriminator is doing that and it requires update. So this is once again when the discriminator weights are adjusted by using the error function. Both gradient generator and discriminator are adjusted by using the backpropagation method. Okay? The objective function of GAN is actually a minimax value function. I don't actually want you to go with the mathematics, but with this little bit mathematics you should understand actually. So this objective function comes from the two-player zero-sum game principle, and it's a function of the weights of the discriminator summarized as D and the weights of the generator encapsulated inside this G. This E stands for expectation value. Don't be frightened. Expectation is nothing but the average. These X's, X from P data X means these are the images taken from the training data. So we take the images from training data in small batches of 10, 100, something like that. Then we evaluate log of dx. What is dx? Dx is the score assigned to an image by the discriminator. Log of dx is the logarithm of that score. So we just take the logarithm of these scores and just make an average of it. This average is interpreted as an instantiation of the expectation operator in this situation. So this is the average score, logarithm of the average score assigned by the discriminator to each of the actual real images. And then, so this discriminator tries to maximize this portion because discriminator must also be sure that when the image is real, when the image is coming from the training set, it should give it a high score. So the discriminator tries to maximize this portion. Then there is GZ. What is GZ? It is the image generated by the generator. Z is the random noise. GZ is the image generated by the generator. And D of GZ is the score assigned to that image by the discriminator. 1 minus D of GZ is basically reverse of the score. Remember, if something is 1, then the logarithm of that thing must be 0. In other cases, where the score is in fractions, the logarithm is negative. So these two terms are usually negative and their maximum level, maximum ceiling is 0. So log of 1 minus D of GZ, this part the discriminator tries to recognize the generator samples as fake. If D of Gz is very small, then the 1 minus D of Gz will be very close to 0. Okay? So the discriminator tries to maximize this whole objective function. That's why it's max with respect to D. The generator tries to minimize the second part of the objective function. If the generator can generate very realistic images, then D of Gz will be close to 1. Log of 1 minus D of Gz will be very close to a big negative number. So the generator tries to reduce the second term down as far as possible. And this is used as the objective function of GAN. It is minimized with respect to the generator weights, and it is maximized with respect to the discriminator weights. So we can also look, another thing is, generator has nothing to do with the first term because the first term is fully dependent on discriminator. That's why for the generator, the cost is only this much. And it is reversed so that we can describe optimization attempts of both the discriminator and the generator as maximization. Okay? So this is how the GAN training proceeds. We take the gradient of this objective function for the generator, for the discriminator, and gradient of only the second term for the generator. Instead of having negative of this 1 minus log of 1 minus D of Gz, we can simply take log of D of Gz and tries to maximize it. It will proceed in the same manner. This form of the generator objective function is actually better to avoid the vanishing gradient problem. So I will just show some nice results. So this is, here you can see we have a blue ring-shaped target distribution. This target distribution is to be mimicked by the generated data, which is orange in color. And as the iterations are proceeding, you can see the generated distribution better captures this blue distribution for GAN. In case of variational autoencoder, this variational autoencoder is another deep generative model, but here the mimicking of the fixed distribution is weak and still, there are haphazard points. So what we see is that GANs are not meant for estimating so much easy two-dimensional distributions. GANs are meant for generating objects from various classes in this manner. So in this picture, you can see the horses, the sofa sets, the buses, the churches, none of which actually existed on Earth. The cycles which never were manufactured, the trees which never were grown. So that's the idea of GAN. It can generate such artificial objects, and how the GAN images evolved with time. In 2014, when we did not have the luxury of using large GPU clusters or tensor processing units, at that time the GAN image used to be hazy, not so prominent. But since 2017, and especially now with the progressive GAN and big GAN projects, you can see so realistically generated images with all the wrinkles on screen, the pimples, expressions, gray hairs, very appropriately visible. Do you see that? Not only human faces. The recent Big GAN project from DeepMind can generate images from the classes of ImageNet with much better than before quality. So this pasta, this dog, this shooting star, bubble, coffee mug, space shuttle, they are all artificial, generated by GAN. That's how GAN is used. Every week, almost a new GAN paper is coming into picture. In GitHub, you can see this GAN Zoom, which is basically a repository of very interesting GAN papers coming up very recently. And the research on and with it is mounting. I will straight away skip some slides because I don't have enough time. I have another meeting to attend and go to the future. Another very interesting work for the future research, which you can see and with which many works are going on, is the cycle GAN. So cycle GAN appeared in the ICCV 2017 conference, which is one of the largest computer vision conferences. One of the two, the other one is CVPR. So in ICCV, this ICCV paper They showed how GAN can be used to import the style of one image into another image while preserving the content. So the paper begins with this picture actually. So if you look at this picture, it clearly says cycle GAN is such a system where if you provide a clicked photograph and if the cycle GAN is trained with the drawing strokes and the image styles by famous artists like Monet, Van Gogh, Cézanne, Ukiyo, etc., then cycle GAN can impose the drawing style of these artists into your photograph. And you can see how your camera clicked photo would look like if the same landscape would have been drawn by Vincent van Gogh. Cycle GAN can convert photos into sketches, zebras into horses, summer into winter landscape, and rivers. That's a remarkable idea which now people try to imitate in voice also. So can I impose the voice? This has great applications in special effect, in computer graphics related special effect in movies industry, also automatic dubbing systems and so on. How I can impose Amitabh Bachchan's voice texture into my content. So this lecture will be by myself, but the voice that you will hear in the baritone will come from Mr. Bachchan. How about that? It's a remarkable idea. Similarly, GAN has many other cool applications in e-commerce, generating high-resolution photorealistic images, neural photo editor, it's a behavioral photo editor. So you keep your cursor somewhere and it will show how your hairstyle can automatically adapt to the traversal of the cursor. Okay? Similarly, another image-to-image translation system is the pitch-to-pitch system, where it can generate actual output street scene just from some infrared imaging or just from some schematic imaging. Similarly, it can convert a black and white input to a colored output. It can generate actual objects from sketch, etc. It can generate a map from an aerial photograph. So many applications of these things are nowadays there. So in Amazon, you will see virtual trial rooms. You upload one picture of yourself and also you buy a jacket from them, try to buy a jacket from them, and they will show you how you look like in your picture when you wear that particular jacket. This is another nice application where you can impose your own expression to one of the old or an archival photographs, like how Mona Lisa looked like if she imitates one of your facial expressions, right? So this is what this particular paper, few-shot adversarial learning of realistic neural talking heads model. It's a paper from I think 2020 CVPR. So this paper describes this nice application of GAN, bringing older photos to life. Like all other domains of science, GAN can also be used for good and bad purposes. Deepfake is a project which generates fake images, fake photographs by using GAN, and it was done to make people alert that this way fake news can propagate through social media. So GANs can be used for such bad purposes as well. It can generate fake news, fake video clips that can trigger a riot somewhere. So like all other branches of science, like the atomic energy, we need to understand GAN is also a two-edged sword, and we need to use it carefully so as to utilize its bright side only. This is the picture of Geoffrey Everest Hinton, whose academic children are responsible for this deep learning revolution. After so much research with these deep neural networks, Hinton still believes that we are light years away from how the human brain really believes, how the human brain really works, functions. So that is really remarkable. And in a recent conversation, Hinton has remarked that the future depends on some graduate student who is deeply suspicious of everything I have said. What does that mean? That means you should never stop questioning. Maybe from your questions and your doubts, further new areas and new revolutions in artificial intelligence will come up. So with this, and by showing this last slide, which contains very nice resources for deep learning, you can see this nice book written by Ian Goodfellow, Benjio, and Corville. This is one of the most reliable books and completely freely available. By the way, all the resources, all the papers related to machine learning, computer vision, deep learning are completely freely accessible. You don't need to pay IEEE, Elsevier, Springer, these publication houses. You don't need to pay a penny to them. Thanks to, once again, Geoffrey Hinton and his students and their open access movement, that the entire machine learning literature, even if it is published by IEEE, for example, the CVPR proceedings, the new RIPS proceedings, not the new RIPS, I think CVPR ICCD proceedings are published by IEEE and Computer Vision Foundation jointly, and they are free. Any paper from any year you can access. That's the greatest benefit. So all these resources are free. Many slides in this particular lecture have been gratefully acknowledged from these resources. They are taken from these resources. You can have a look at them. So with this, I would like to conclude. I have already overshot my time because I had a meeting in the morning. So now if you have questions, I can take up a few questions from you.
Any question by the participants? Please quickly ask to the sir if you are having any of the questions.
If you have...
Sir, excuse me?
Yes.
Hello, sir, this is Shami.
Yes, Shami.
So thank you very much for allowing me. My humble request, my humble gratitude to sir for such excellent presentation. I am requesting, sir, sir, would you please be kind to provide us some particular blogs where we can join to actually learn further about deep learning and that sort of thing. As well as, would you please be kind to provide us some blogs where some video tutorials are also available like that? And thank you very much, sir.
Yeah, thank you for the question. Obviously, lots of video tutorials are available. This book is freely available, and there is a really nice blog. There are 2-3 nice blogs, in fact, which explains this concept in a very nice way. One such blog is the Towards Data Science blog, which you can see. Let me write in the chat box. This is the Towards Data Science blog, which you can see. There are a great collection of video lectures in YouTube as well. There are a great collection of chapter-wise lectures from this Ian Goodfellow's blog and other blogs. Let me just try to give you a video lecture link from YouTube. And obviously, I will be happy to share the slides with you later on. So this is the link to the deep learning book. If you look at your chat box, this is the link to the deep learning book. All chapters you can download freely and read them. And this is an excellent. By the way, also let me tell you, when Goodfellow invented this deep GAN, he and his supervisor, he was only 26, 27 years age. By now he's how much? 31, 32, and he's a superstar in this field. So this is his video. And Geoffrey Everest Hinton is the teacher of, I think, Benjio and kind of senior colleague and teacher of Joshua Benjio and Jan LeCun. So this is a video lecture by Goodfellow himself. And another one, if I give you, there is an excellent session by a collection of video lectures by Geoffrey Hinton himself, which you can see. Some are here. The deep learning lectures are fully completely here, which I encourage you to see how this man speaks. He's the person who invented, he and his colleagues, Rumelhart, William E. Rumelhart, and I think another British guy was there. 3 of them actually invented the back propagation learning algorithm for training the multi-layer perceptrons long back in 1986. And that paper was published in the famous Nature journal. So this is a collection of the video lectures by Geoffrey Hinton. 1986, when Hinton and his colleagues published the backpropagation paper, that was actually the birth point of deep learning. Since then, Hinton is repeatedly saying deep learning can do wonders, can create magic in computer vision, etc. People needed more than 10 years to understand what the guy is saying. And after 2012, everyone really turned their attention to it. And obviously, by that time, the computer hardwares got much improved. These GPUs became widely available. One last thing to tell all of you that if you really want to do some meaningful research in this particular area, it's always better to have some GPUs, some GPU clusters, or high-end parallel computing facilities. NVIDIA usually every year opens up for donation of GPUs. Now NVIDIA has acquired ARMs. So we are assuming cheaper parallel computing facilities will be in the market very soon, including this RISC-V and other public license hardwares. So with this, I would like to thank you once again and stop.
Sir, on humble request, if you please be kind to us, please be kind to share your email address with us once again, so that it can be your staff. Thank you very much.
Yeah, this is the email address.
Afternoon, sir.
So I have shared the email ID on the chat box. Should you have any offline questions?
Good afternoon, sir.
Yes.
Good afternoon, sir.
Yes, yes.
Sir, I have one question related to I am using dataset like EEG signal dataset. I am using my work, and whenever I am approached related to any deep learning model, it is going to be require image format like a CNN model or GAN model, LSTM. So how we can convert that signal to image form, sir?
Yeah, I mean, you need to have a two-dimensional description of the signals if you want to use convolutional neural nets or anything similar to that. Otherwise, if you are using recurrent neural network models or RNN models, then you may not need to convert the EEG signals into a two-dimensional format. Otherwise, you need to convert the EEG signals by taking their short-term Fourier transform STFT or wavelet transform, where you will have a time frequency modeling of the signal. Okay, if you do the time frequency modeling, then you are essentially converting it into a kind of two-dimensional description. That would be very helpful. But otherwise, what you could look at is basically the RNNs or recurrent neural network models, like the Boltzmann machines now and its variants, which is a completely different but still deep learning paradigm that I have not covered. These are not convolutional, and they can very nicely handle such single-dimensional sequences. In fact, one-dimensional convolution is also possible, but that doesn't always give you the rightmost results. I am sharing a review with you for your perusal. It's a nice review on the developments of EEG signal classification by deep learning. So you can go through it. Look at the chat box.
Kindly, sir.
Already in the chat box. Yeah. Okay.
Thank you so much, sir.
Okay, sir, as you are running with a short of time and you have a meeting lined up, so I take this opportunity to thank you, sir. We are very much happy to have you with us. You have enlightened our participants as well as to us. It's the concepts of this GAN. Actually, GAN has been more booming word as I have the knowledge about it little bit. So it's very interesting, sir, that you have presented a very elaborated description about this GAN. So thank you so much, sir. We are happy to have you again, and we look forward to get assistance from you in future.
Thank you,
sir.
Thank you. Have a good day.
Thank you. So dear participants, it's a humble request that whenever a talk is going, please maintain the decorum of the session, please. If someone is speaking, he is there to address you. Please do not interrupt or please do not give the information that could be asked at the later stage. Please, it's a humble request. Please do not repeat it. For the questions that has been asked, it's like we would be providing you the certificate by the next week for sure, as we require a director sir to be available in the campus as well as the signatures in the certificates. And as we are coming to the end of this 1 week STC of soft computing theories and application, I, Dr. Nisha Chaurasia, along with the Dr. Mohit Kumar and our convener, Dr. Adversarial Singh, as well as our head of the department, Dr. Renu D, takes this opportunity to thank you all, one and all, for this attending this STC. It was our active participation from your side, and we are happy to see that you are actually having a good time. You had a good time with our experts. I hope the feedbacks have been received, feedback link has been received to one and all, and we would be happy to see any suggestion given from your side, and we would try to address that particular concern. So thank you one and all. Thank you everyone. Stay safe, take care. Yes, sir, you can leave now if you are willing to leave. Thank you. No, sir, this was the last session for this STC. Thank you.